Always good to have a movie to start. So, ladies and gentlemen, welcome to this special event. We have been a bit overwhelmed by the number of people who wanted to attend it, so we have an online session in another room. Also, welcome to everyone online. And we have this special lecture on life on Earth and beyond. And this is really special because we have two fantastic scientists and renowned personalities in Switzerland and abroad. These two personalities have joined ETH within the last, Didier, 2 years? 2 years? And 1 year. In principle, I shouldn't need to present Thomas Zurbuchen and Didier Queloz. But I will say a few words how we met, because I think it is interesting. It's joining, personalities meeting, but also projects. I start with Didier. Didier, I was at Webb, and my staff, Jörg Brunschweiler, came to me and said, there is somebody called Didier Queloz who wants to talk to you. I said, immediately. And then he came and he wanted to talk about a project that he was launching in Cambridge on life, search for life outside of the solar system. And it turned out I had my computer. I opened my computer and I showed a project that 5 departments at ETH have been putting together exactly on the same project, on the same topic. And this is where we started to discuss. And at the end, after a few meetings, joint workshops between Cambridge and then ETH, then it became clear that we should do something together. And this is how he joined ETH 2 years ago. I'm very happy to have you here, Didier. And with Thomas, a little bit the same thing happened. You were here to get the Doctor Honoris Causa. And then a few months before, you know, at the ETH talk, always we give these prizes. And then he had just announced he was stepping down from his position as science director of NASA. And then as usually, very directly, I asked him, what are you going to do in future? We are here for you as well. He asked me to wait until January, which we did, and then we started to resume discussions. And also here, we had a project launched by Vanessa. I asked her to look what we are all doing in space at ETH, and it turned out we have so many groups in so many departments working on this, but it was not so well known. So we wanted to create a new initiative along this line. And presenting this, probably we could also convince Thomas to join. So those are two fantastic recruitments that we could make, and we are really excited of having you here at ETH, Didier and Thomas. Thank you so much. Now, why we have this event? Because, you know, the mission of ETH is very broad, and I put it sometimes in a very simple way. But we have 5 focus points. It goes from the fundamentals all the way to dialogue with society. And we have, of course, here 2 fantastic personalities that can have the dialogue with society, with you, with everyone. Then we have also the goals to address the global challenges of our time, be it on AI, be it on environment, energy, be it on health, personalized health. It turns out that these 2 personalities and the 2 programs that we are launching at ETH, they are addressing each of these different points. Let's take an example. Monitoring of Earth, of CO2 emission. This can be done at scale only using satellites. And this is one of the projects that we are pursuing and that we are also fundraising together with Thomas. The fundamentals, one of the biggest remaining questions, how is life has originated? Is there life outside of the solar system? Also, very big question also as humans to know the answers. So it goes from curiosity-driven research all the way to impact-driven research. And this is exactly what we want, and I hope you will address this point here. So I'm delighted to have you both here in Zurich. I'm convinced that we have a fantastic opportunity to build something extremely strong around these two initiatives for Switzerland, but not only for Switzerland. I say the mission of ETH, when I put it really simple, is to serve society, and not only the Swiss societies and the world at large. We will increase our level of cooperation with various universities in Switzerland, and we are not talking about this, but there are people coming all the way from Lausanne here. Welcome to everyone. And I mentioned at the beginning we have two outstanding personalities on stage. Actually, we have three personalities on stage, because it will be moderated by Anna Maltsev. Anna has been here for 10 years now. It was always fantastic pleasure to have you working with you for all what you are doing. You are pushing this communication on these two initiatives, so thank you so much. Now I pass you the word. Thank you, Anna.
Hello, everybody, and also from my side, a big, huge and warm welcome to all of you here at ETH Zurich, and of course also to everybody who's watching wherever you are right now. My name is Anna Maltsev. Thank you for this nice introduction, Joel. I am one of the spokesperson of ETH Zurich and the editor-in-chief of the Employers magazine. And I couldn't be more happy to do the moderation tonight, because from my point of view, actually there is no more exciting question on Earth than the origin of all of us, right? The thing that connects all of us, no matter where we live, no matter how we look like, no matter how different our opinions are. This is our origin. And also, of course, like life beyond Earth. Are we alone in this universe? It's, for me, the most exciting question ever. So I'm really happy that I could support both of our space stars in the last years with their communication, and now can discuss with them these amazing questions. We're gonna discuss them like for about 1 hour, 3 of us, and then there's gonna be half an hour Q&A session. So just keep in mind, in the end, you will have the opportunity to ask questions, whatever they might be, about life on Earth, origin of life, life beyond Earth. But before we start, and I welcome our 2 space stars, I would like to show you what we actually do already here at ETH Zurich in the research of origin of life and life beyond Earth. I was walking around a little bit the last weeks, and we made a little video trailer. Yeah, I hope you like it.
To me, finding life on another planet is the most important question we could be working on right now in space, and frankly also on Earth.
30 years ago, we found the first planet orbiting another star. That was a monumental discovery that kick-started a new field that we call now exoplanet research. And that's the reason why we have established this center with about 40 professors here working to different disciplines. And we believe that it's just a matter of time until there will be some answer about the question of, so why do we have life in the universe, and are we alone in this universe to be alive?
We can get to half the temperature of the sun. It's like when 2 planets collide, then you would reach these sorts of temperatures. We try to create the conditions during the birth of the planets in our solar system and those around other stars.
My group and I were looking at life that lives deep underground. These are very simple organisms that live just by breathing rocks. Studying these very simple organisms, we're learning a lot about how the earliest life could have evolved and what life may look like on other planets.
At NASA, I developed instruments for the detection of signs of life on other planets and moons within our solar system. And now, as part of ETH Zurich Space Masters program, I'm excited to share this knowledge with the students so they will hopefully detect life beyond Earth in the near future.
With my team, we find out what we can learn from the James Webb Space Telescope, not only about the atmospheres of planets, but about their deeper interiors that are coupled to these atmospheres. This is very novel, and it's necessary to understand whether there are other worlds that can host life.
The life mission we're developing will allow us to detect dozens of planets that are similar to Earth. And then we can search for signs of biological activity and address one of the most fundamental questions of humankind.
What is life in the universe? And how far the life on Earth is related to life elsewhere? So we will really try all what we can to understand this. And hopefully that will be useful for humankind.
It will be very hard to imagine that there's not life outside of Earth. I believe there is, but at this moment in time, we do not know. At ETH, we can make huge progress towards answering that question.
Thank you very much. So, and now a big, big and warm welcome to our two space stars, Didier Queloz and Thomas Zurbuchen. Welcome.
Thank you.
So amazing to have you here at ETH, to have you here in this discussion. It's like a really huge pleasure. So, but before we go and dive deep into the origin of life, I would go and dive a little deeper to the first I need to mention is please take a look at these socks. I'm so sorry, but both of them have just the most amazing planet socks I've ever seen. And it's like...
I don't have any.
And it's like, no, so I would actually would love to ask, because Thomas, you have always planet socks. Like, why? I was wondering so many times, what's the story behind the planet socks?
Yeah, I always said the most interesting thing about me are my socks. Yeah. But what happened, in my previous job, what happened is all my suits were new because I never wore suits before. And it was really quite clear that I needed to be kind of dressed very formally because any day I could go to Congress, so I needed to be in a suit and kind of nice tie and so forth. So the only place where you had liberty to kind of show off, kind of without kind of being visible about it, are the socks. So I threw away all the black socks, and every single pair of socks were new. And frankly, what happened, it created a whole bunch of businesses. So basically, like these socks I never bought. Somebody sent it to me. It's like, thanks. It's my business to do space socks, and he has a whole business next to his wife, who's an astronomy professor in some university, and a Dutch guy who's doing that. And so I have a whole drawer full of socks, and I just use them one after the other.
Do you have also a story about your socks? Or
well, my story is very simple. I know I would be sitting next to him, so I had to wear my socks as well.
Love it. So, let's go deeper a bit into your interest in not just in space socks, but in space. So I found it so interesting, actually, your story. You're like both Swiss guys, right? You're almost the same age. You grew up in different parts of Switzerland. What we can see here now is, maybe someone can recognize it. It's Heiligenschwein.
I do.
You do for sure. This is Heiligenschwein, where Thomas Zurbuchen grew up, not far from Bern. And then we have here a beautiful part of Geneva where you grew up, Didi. And then you both flew around, somehow made like huge positive impacts in space. Like you won a Nobel Prize, you've been to NASA, been the research head. And then you both came back, right, in this beautiful place here at ETH Zurich, met again here. And actually, during this time, you kind of found the same big research goal, or maybe also life goal, to search for the origin of life and for life beyond Earth. So I was wondering, how did it start? Maybe Thomas, how did it start for you?
I mean, for me, growing up in a small town, pretty isolated from industry, has huge advantages because the sky is very dark. So what you can do is you can look at the sky and see things move. What's so interesting about the sky, it's actually not the same every night. And as you look at it, you see things move. And if you're lucky, you see transient events that are happening. And it makes you think. Kind of looking at the sky starts with questions that you then can answer with science. For me also, growing up there kind of felt a little bit confined because of the environment I grew up in, this kind of environment that I was in. And public education in Switzerland kind of really started to help me ask those questions. And then not just science. See, for me, some of the things that were really important are questions about history. Like, how do we change our opinion as humanity about something? The opinion that we're the center of the universe and the bosses on it, whether they're religious or bosses or kings. How do we get from there to a place where we know, that is not the case? And for me, the tools were science. So I got really excited about this. And, I really give all credit to the public education system because that was not discussed at home. And so the public education system opened these doors, and then, what I had to do is walk through it. You have to walk through open doors. That's an important lesson. There's a lot of open doors many places, but you got to walk through it and actually do the work that it takes on the other side of that door to kind of find the next door. And so I had fortunate experiences at many different locations. That's my story. It's one of public education and a dark sky.
That's a beautiful one. What about you?
Well, there's a lot of similarity, but I think the main incentive that bring me here is, I would say, my unusual level of curiosity. I'm extremely curious, and it never stops. And I was so curious that I didn't really know what to do with that. And I went into physics by lack of, deciding what to do. I thought physics would bring me even more curious. So I went into physics, and I really literally fall in love by research. I realized I was exactly the level of feed that I needed to feel at ease. So my level of curiosity is a bit annoying because it never stops. So I still have the same level of curiosity, though by the time you develop more knowledge, you always set the bar higher and higher. And right now I have this impossible goal to find life. So this is because my curiosity level has reached this level. And that's why I am. And that's the reason why I'm still working in kind of a world which is addressing the questions of how do you search for, how do you prepare the future of the knowledge, and that's it. So I could have done other science, I guess. The fact I was maybe a little more gifted than usual, students for math and mental pictures drove me naturally into physics. But it's just curiosity-driven, really sincerely here for me.
Yeah, I think we're all very happy that you didn't choose another one and you're here now. Then we have these beautiful 3 pictures here, which you sent it to me, Thomas, when we were discussing about why is it so important to you and why do we have this big interest. So maybe you can explain us why did you choose these ones?
I think I already started kind of in many ways what excites me. And the reason I studied physics, I also, like him, had a hard time figuring out what to study. And not because I just was interested in too many things. I read many more history books than science books for a long time. And for me, and still do, I read a lot of psych books too. Kind of for me, it just really, I was interested in that. But it's a class that was focused on the Copernican revolution that kind of made me want to study physics, and then kind of really understanding this story that is in these 3 pictures. Of course, all the way to your left, you see kind of a toy that Galileo was given, sent from Amsterdam. It's kind of 2 lenses in a tube. And kind of when you look through it, it looked like something came closer to you. Galileo, of course, then pointed that out and started discovering the moon and its shadowy parts, kind of the landscapes on the moon. Looked at the sun, also found spots, which, by the way, you're not supposed to say, because the sun at that moment in time was kind of so often in church used as a sign of God. So spots on the sun was no good from that perspective. But what he also found, and you see the note on the right there, what he also found is that if you looked at Jupiter, there were other celestial bodies that moved, and clearly about Jupiter, not about the sun, not about us. It's about another body. Once you realize that, you realize, wow, things are really screwed up in a picture in which we're the center of the universe. These bodies don't know that the Earth is the center of the universe. They think Jupiter is. So clearly, the one thing he did that's different than this Polish scientist called Copernicus, what he did that's different, he talked about it. And it did not end well for him, right? Kind of with all the house arrest. Some others, of course, Giordano Bruno, some others ended up one head shorter. In this case, he had a house arrest. But remember, kind of building a tool, kind of using a tool to discover the sky anew is really what I think is some of the coolest things we could be doing. You can't do that. Like today, you can't get these tools from Amsterdam in a gift bag. You have to invent them yourself, whether it's a telescope or whatever, kind of a new type of telescope. But we can do that. And we should do that. We just heard Professor Quantz talk about this in other ways. We should do that. That's what my story is relative to that, kind of the motivation of, hey, yeah, we can discover the sky anew by using some of these new tools.
Beautiful. So let's switch over to from your origin of interest to the origin of life. Actually, it's the big center which you just started about 2 years ago at ETH Zurich with now more than 40 research groups just at ETH Zurich, right? So I was wondering, where is our stand now? What do we know at the moment? What is the leading school of thought?
Well, I mean, it's interesting to go back on the way this went through that level right now. I mean, in science, when you look back at history, talking about history, there are special moment, a bit of tipping point. Something is going a bit different way and it's changing the trajectory. It does not happen always, and it's quite often the result of maybe the technology, telescopes, maybe a kind of a new mathematical tool, or maybe we see something that we're not supposed to see and that was unusual, and then we open a new window on the universe. So what's happening here is quite interesting, because 30 years ago, we came with the first evidence that there are planets orbiting other stars. No, it's common. No, it's amazing right now, and it seems so obvious. But if you go back 30 years ago, that was really not obvious. And it seems amazing how so quick we have already captured this reality of our world. And science is full of this. And this kick-started kind of a slow momentum here, where we started to look for more and more planets, and the piece of luck in a sense that the universe was kind with us, because they produced so many planets that was within the capability of our techniques that is still very limited compared to what is going to happen in 50 years or 100 years, that we keep finding just so many planets, and some of them very small, and some of them that not exactly like the Earth, but where you can ask yourself, well, maybe there are some atmosphere, what's going on there? So all these questions of whether there are planets with something going on moved from something that you would see in the sci-fi movies and to a real scientific fact. It's a reality, it's something we do see. And then in parallel, we have seen this moment change into our capability to explore the solar system. So again, go back in time. I mean, it was only 50 years ago that people went to the moon, and it's nothing 50 years ago. And how much probes we have sent, and now we have studied the solar system and the level of understanding we have, and we still so more we can do. And then the question is valid. Can we look for a sign of life in the solar system that may have been a bit crazy in the 70s, but attempted, but now it becomes really real? I mean, there are landers, there are sample return. And then the chemists have completely changed the perception we have about life. Think about just 20 years ago, doing the whole DNA scan of a human body will take thousands of scientists, 1 year. It was a big momentum achievement. Right now it takes 5 minutes, essentially. So the capability to study very complex chemical reactions has multiplied manifold, and the understanding we have on the functioning of life. So all this goes together, and now we reach a level when all these disciplines start to look at each other and say, oh, but maybe I can use my chemistry to look at something on Mars, or maybe we can look at another planet, and so on and so on. And this is the beginning of the new level. This is the tipping point where we are right now. We can now set as a goal, which is not a dream, that's a real goal, that we will collect facts and understand how you move on a planet from a planet to a planet with life. And this is where we're sitting, and this is what we have established in this place, because it happens to have a lot of people that have interest for this topic and have the expertise on some element of this big jigsaw that you have to solve. It's a bit of a long answer, but that's really where we are right now at this place. And that's the main reason why I came back. It's not because I came back to set up the stuff. I came back to help setting up something that was already going on here, because people were already working on that. So it's really kind of a science into motions. And I can tell you, it's tough, but that's fun.
Do you mind if I ask a question? I always wanted to ask you. Now I have a few witnesses. So the one thing that was crazy about your discovery that you announced in 1995 was that the 2 planets that you found defied every model that was out there and was taught about planetary sciences because it was different than any planet we had in our own solar system. That's, of course, why other groups across the Atlantic and others, they had data too, but they rejected it. They didn't even look at it. What gave you the guts to look at it and just basically say, even though every model is wrong here, the 2 planets? Could you tell me how that discussion went with you and your advisor?
Well, and it's an interesting question, and that's something that I try to explain to all my PhD students, is the detail matters. So when there are things that is a bit unusual, this is where science starts to be fun. And it's exactly what has happened. It didn't happen exactly on the fun side, because at that moment, what came up out of the data clearly was not expected. And of course, when you have this happening, the first things you think about is something is wrong, really wrong with it. And you have this kind of a panic moment, there are something really wrong and you don't understand anymore. But then it's rational thinking. So you address the situation point by point, element by element, and at some point this detail becomes a fact. And you cannot put the fact under the carpet. The fact has consequences. You use a law of physics that you know, you apply them, and the consequence of this fact, there is a planet orbiting that star that, I agree, was not really the planet everybody was expecting, but we had so few planets. We had only the planet of the solar system. So when you come up with this conclusion, we said, okay, it is the situation we are in. There is no other explanation. That's really the trick here. We have no other way to explain this very solid fact that we have. And that's true that essentially nobody believed us for a couple of years. Yes. It has been really a very difficult time. And even for me, as a young scientist just with a PhD, that was clearly something that you're not supposed to do. And you never do that. It's crazy. And it took, I think, 10 years for me to really reach the level when I was start enjoying it in a sense that as accomplishments. Because for a long time, and that was seen as an awkward situation. And I think what changed completely the game is the space mission Kepler in US, that started to look at, millions of stars, 1 million of stars, and no, it's 100,000 actually at that time. And then they start detecting hundreds of planets, and they were all so awkward than the one we had found, all this super Earth and mini Neptunes, all stuff. And then at that moment, everybody understood, yeah, there is really something really that doesn't work in the way we understand the solar system. And that is the tipping point when, a bit like you start to find out that the Earth is not, the center of the solar system, and then you're orbiting the star, is, but it means the solar system is one amongst many, and what does it mean? And that is a bit the situation we are in. So we started one way, but the start was just the beginning of a long series of events that led to the conclusion that, well, we have completely misinterpreted the situations like people did before Galileo by setting the Earth on the center of the system, because it's obvious when you look at the sun, it's moving, but it's not that simple.
Yeah, I think I just want to make one more. So I think it was gutsy. Mm-hmm. It was really gutsy. The one thing I wanted to just add to the searching for life in the solar system you also mentioned, there's something that's really interesting to remember, and that is that there was the Viking missions, 2 landers on Mars that actually really tried, kind of in the, 80s or something like that.
77.
70s, tried to basically go search for life on Mars because it's the obvious place. And of course, the question is, how would you find life? Kind of a few scientists came together without any real data other than kind of thinking that they did experiments, and of course, there was no life. because you didn't know how to ask the right question. So sometimes kind of a leap of the type that you did, really just broke open the door, and kind of we know the most abundant planets we have none of in our solar system, right? But sometimes kind of you try to do a leap like that, you are a little bit less lucky. It killed kind of searching for life in the solar system for decades. And kind of the strategy that opened it again was a much more sequential strategy. Let's first look for water. Oh, there's water everywhere, holy cow. And then the water below the surface of these moons. Oh, there's ocean worlds, gosh, and so you keep, and then you etch yourself to it. And today we know we would build really different instruments to go find life on Mars than were built there. So it's kind of two different stories kind of converging at that, as you said it well, a pivot point, tipping point you called it, a tipping point of thinking and really a beginning of new research.
Yeah, and I think a beginning of new research was also started when you launched actually the James Webb Telescope, right? One of your biggest or the biggest project when you were at NASA. I just took. This is like my favorite picture. I know you have another one. And sometimes I think like when I look at the pictures, the photos of James Webb Telescope, I always have like so beautiful feelings. And sometimes it's just my personal theory. I think it's also maybe because we kind of can look a bit back in our origin. I don't know, but what do you think?
Oh, without a doubt. What you're looking at when you look at the stars is your history. Without a doubt.
This picture, if I may, is very fascinating because this is the beginning of the story. I mean, this is the molecular clusters. This is when you have all the gas that is going to be used to form then the stars and the planets later on. But this is a factory, and you make the water. So the water is being made into this machinery here, which is not so far from us. We're not talking about something very far away. This is in the galaxy here. This is really the beginning. It's big understanding. You start somewhere and you move somewhere else. But the water you form here would lead to nothing without the planet. So the planet is maybe the detail of a story, but it's an essential story if you want to make life. So water is good, but you need some place to use the water. That's the reason why you need planet.
The one thing that I also see in that thing, so the way I always talk about it, it's like a hospital. Like you said, it's kind of where stars die and new stars get born. That's what that's what you're looking at, and I always remind people. Carl Sagan said it well. We're made out of stardust. Kind of every atom in our body is at least 1 billion years old, and then you look at the stuff that the stars give back to the space around them, from which new planets form. But new stars form, new planets form, and what we know with the James Webb, since we look at this. It's this stuff that you see that's brownish there. A lot of this is organic material. So it's not just single atoms. It is water, you're right. But it's also much more complex organics, many more complex organics than I was told in my astrophysics class.
Right.
And so for me, if we look at now primitive bodies, as we call these, there's nothing primitive about asteroids, about comets. You look at these bodies, so many. We're surprised how complex they are chemically, which is what you see here. So kind of like what you should think about when you look at this brownish yellowish things. This cometary material going to happen, right? That's kind of where it all comes together in our world. So that's the beginning of the solar system. Kind of came from one of those yellow brownish splotches here from stars that went to die in our neighborhood.
And then I have also your favorite James Webb Telescope picture. Maybe I've just in a few words, because you told it once, and I really liked the explanation in an interview with, I don't know, the Kirchenblatt, I guess. But yeah, it doesn't matter. What can we see in this beautiful picture?
I think for me, it's just the magnitude of what we see. So kind of, if you looked at this picture in the sky, let me just tell you, if you put a grain of sand on your hand, stretch it out, you could cover all of it up. So it's all behind the grain of sand, covered, grain of sand covering on your stretched out hand. So it's basically nothing in the sky. That's what you're looking. By the way, anywhere you look, you see this kind of stuff. And so if you went and counted how many galaxies are behind that grain of sand, the answer is more than 6,000 galaxies. Some of them, and there's one of them that made history, and I could go find it for you. It's a tiny little red dot. The light from that galaxy has been in the universe coming to us at the speed of light for 13.1 billion years. But many other historic galaxies are there. Each one of those galaxies, by the way, has of the order 100 billion stars, perhaps up to 400 billion. So the point is, what you're looking at is billions, 1,000 billions of worlds that are there, and every one of those stars on the average has a planet or more. So just think of that, behind a grain of sand, that much wonderful nature. That's what I see in that picture. How about you?
Wow. You see a lot. Well, this is what we call the cosmological picture. So this is this this message from the very far in time, because we have this time travel aspect. This is the moment when there's a lot of question behind that. When you form the first stars, when you establish all this complex chemistry which is made into stars, as you said it rightly, and that is happening and producing all these elements later that will lead to life. So it's part of this long chain of events. What I like thinking about this is the beautiful behind all that is the law of physics are the same. When you look back in time at something which happened in 10 billion years ago, for this picture typically here, is the same law of physics. So there is some kind of magical element in our galaxies, because the law of physics is such that enable this, they enable the stars, they enable the chemistry, they enable the molecular chemistry, they enable water, they enable planet, and they enable life. They even enable the consciousness right now we're using for this discussion. So it's all into this universe, it's all following the law of physics. So potentially, all these elements, we should be able to understand something out of that. So that's why I'm a strong believer that we will find out why there is life, because it's embedded into the law of physics. I'm not the first one saying, and Christian de Dieu was the very first one mentioning that, that there is a reason why we should be able to understand that, because there's nothing different in terms of physical behavior, just more complicated to deal with that. But as it was complicated to understand why the sun was shining, well, it took a long time to understand. No, it's obvious, we know why, we can just predict what's going to happen. But to do that, you need to do a lot of equipment that's going to understand what is the atom and how it works. So we're going to reach exactly the same level. It's this beautiful element of the power of the brain that has the capability to build tools that go much beyond simply the obvious element that we can grab with your fingers and with your eyes, but we use this brain. The brain is just a fascinating tool. It's the most powerful tool we can think about in this universe right now.
So the universe makes a brain that thinks about itself.
To think about it.
That's so true. And the universe makes also some exoplanets. And actually, I told you this afternoon, I wanted to talk with you.
I love this picture.
Yeah, me too.
Because this is exactly what we don't do. We don't have pictures. I mean, very, very, very few planets we have pictures, and certainly not that kind of picture, which is a result picture. To get that, you need to look at objects in the solar system. This is exactly what you can do. I mean, it will take a long, long time to build up such a picture. I don't know exactly, but the size of the telescope certainly would have the size of the Switzerland, I guess, about to reach this resolution here. So it takes a long time to make picture. But the beauty of physics, and I keep telling that, you don't need to see the quark or the atom to understand the foundation of the standard model. You build an equipment which is amazingly complex at the CERN, which is going to understand all the structure works and produce the Higgs, and you see all that stuff. But you see it through the detector. We don't need to just see it with your eyes. And it's the same everywhere in science. There is this layer of amazing complexity we have built up to translate a mental projection we have, which is what we have here. It's an artistic projection of a planet with what we do. So we never do that, but we detect for sure planet, either by looking at the motion of the stars or looking at the shadow when the planet goes in front. And that's why we know the mass, the size, and we can use a lot of the tricks here to extract during the shadow event the atmosphere, and we can compute the density, and then we can compare with physical model going on Earth in the labs to replicate somewhat we see. So this is the beauty of science, is this projection. So in a way, this is right, but it's just a mental picture which is painted for ease of understanding what it is.
Just that you understand, I Googled first exoplanet and then this came up. So I was hoping he's going to tell me how he found this one, but well, it's not. So don't trust Google. That's maybe the lesson I've learned a few days ago. So let's move on to life beyond Earth. And I was wondering, like many people may know, you both, or we saw it also in the video, you're pretty sure that there is life beyond Earth. But when and how did that happen? Like, when did your belief start that we are not alone in this universe?
I was hoping we were not alone. By the way, we still don't know. I mean, I think we try to say it there. Kind of, you ask us what's our guess. And I'm guessing it's really hard to imagine that kind of every time we thought there's something special about us, kind of in a cosmic sense, we were wrong. I talked about one example where the sun is in the center. Then you understand, we're only one galaxy. Many people miss, right? We thought until the beginning of the 20th century that there's only one galaxy, our own, right? Kind of the many galaxies I just talked to you about, 6,000 in one pictures, that beginning of the 20th century, kind of just started the idea there's other galaxies, right? And so kind of we just tend to be wrong when we think we're special. That's a good lesson sometimes also, standing in line somewhere. I'm not good at lines. But,
well, I certainly have the same way than you, Thomas, on this. But this, my rationale behind this is even more simpler in a sense. I mean, you can think about, okay, we heard about the number of galaxies and planets. It's an amazing number. So you can simply summarize this as a lottery game. So there is a number of lottery game, and you pick and you find life, you don't find life, you find life, you don't find life. Well, that's a statistical perspective. I think the statistical approach is irrelevant in this game, because let's imagine you know that some number will be winning. You know that in advance, because you know this number is going to produce life. Then it shrink a lot the statistics. So we have some ideas of the kind of chemistry we can look, and the condition we can look, and then we can summarize this and trying to get it closer to the reality. How many of this planet may host life? What are the conditions for life? How does it work, the chemistry of life? And it turns out that chemistry of life is just chemistry. So it may well be that you produce a lot of life. Maybe we have life already in the solar system, on Venus, on Mars, on other places. But the fact you start the chemistry of life doesn't mean that you will continue the chemistry of life. Maybe you start it and it dies. I think we sometimes forgot that chemistry is just chemistry, so nothing protects life to disappear entirely for this planet if the conditions are not met anymore. But I do think there is so many possible conditions, and the chemistry is robust enough that if the conditions are met, you should create life. Whether you would create life that will grow and develop, and that will go out on continent, whether you have continent on a planet, whether you can reach the level when you can have a level of consciousness and you build rocket and you start to explore the other stars, that's a completely another question here. But the question is whether universe create life, I'm sure by plenty. There is tons of places when you make it, but it may well be that you don't sustain it very long. And that's one of the questions we're going to find out.
And yeah, that's a good point. Let's go a bit more deeper into the detail. What do you think? On which planetary body, not the Earth, of course, on which other planetary body in our solar system we could find life, or there have been life maybe and died already? Thomas.
We're looking in many different places as humanity. And I think one of our audience members built an instrument herself with her team looking some other place. It's on the way there. It's going to take a few years until it's there. A moon out there by Jupiter. But the obvious place to first look, especially for extinct life, is Mars. It's the obvious place to look. It's kind of funny, you go to conferences, the Mars becomes fashionable relative to life, and then a little bit less fashionable, and then more. We need data. Just like, we need data. Mars is the obvious place to look. The other places are these ocean worlds. And, if I had like $1 billion extra, I didn't know what to do with, or a few billion, I'd go to Enceladus. It's a place that is not explored enough, but we already know that it spurts out water, it has organics in it, and there's a lot of things, the contact of the ocean with the bedrock that really tells us that's interesting. Europa is another one. So for me, if I had to bet, my hope is Mars, but it's much more interesting if the answer is the answer is Europe. But this is the Mars sample return architecture, which is being talked a lot about right now, and it's because NASA is enormously challenged by it. And I said I should have stayed, by the way. They would have been challenged also. I made some of the mistakes also, but you know, kind of what this reminds you to do this kind of bringing samples back robotically ahead of us bringing people there is really, really hard. James Webb Space Telescope was really, really hard. This is also really, really hard. But we're in the process of collecting samples that we would want to bring here to Zurich and some of the best labs and analyze kind of their organic content. And we know it's organic already. We have enough science instruments on the rover to actually analyze that. But so for me, that's exciting. Do you think there's life on Mars, or used to be life on Mars?
I think I would agree with what you said. There's just another element to me which is also interesting is the question is how the evolution of the planet. How much do we understand the evolution of the planet or the solar system? I think the Earth is certainly the one we understand the most, but when you look back in the past of the Earth, the first 1.5 billion years, not very much. So there is a kind of a black hole here in what happened early on into the early Earth because of the plate tectonic, everything is gone. So for that reason, Mars is great, because Mars is the imprint of the first billion years and possibly with water at that moment. But there is another planet I'm fascinated about, we don't talk very much because it's even more challenging, I think, than Mars, is Venus. Venus is the closest planet. Gravity-wise, it's easy to go to Venus. It's the same mass and same size than the Earth, almost. But of course, the situation on the surface is completely different here. But the Venus question is why Venus is like it is. It's quite interesting, because why do we have such a nice amount of water that stays stable about the evolution of the Earth on Earth, and the water is gone essentially on Venus, and we don't have any more plate tectonic. So this is, to me, a foundation question as well. It's not about finding life only, but understanding this kind of lottery game. What makes a condition of a planet suitable than to think that there may be life going on? To me, all the questions are valid. So you can look for sample return and ancient life on Mars, and I think it's a great idea. It's a fantastic mission. So you can look for other chemistry on other satellites, because it's not the same chemistry you would expect. You don't have the water. You have other ways to just other solvents over there, but that's possible. Certainly, you can test some of the very fascinating chemistry. Whether you would recognize anything alive is not sure, because if you don't even know what you look at, but you can certainly study the chemistry. And then we should understand Venus. So I have a great program for the next 100 years here on exploration of solar systems. So I hope that people will go to that. But Venus is challenging.
You know what I love about Venus? So there's 4 missions being developed for Venus. You know, 2 by NASA, 1 by ESA and NASA. Let's not talk about those. The 4th one is by a guy who built a rocket company from New Zealand. And he basically is building an instrument all by himself, because he said, I want to be part of that amazing exploration. I mean, the guy, like I said, it's great to build rockets. I built many. Peter Beck is his name. And Peter basically said, I want to be part of that thing. So he self-financed this experiment. And he, you know, is getting advice from a bunch of scientists. And for me, I love that, because it's so little is known there. It does not take $1 billion to make progress. Massive progress. And so for me, I just absolutely love that. We can do that too. We can do that too. We don't have to build $1 billion telescope, or $1 billion experiment to really make progress in some of these areas. And just, go with one of those rides that are now 10% of what they used to be to space, and then go hang a left to Venus. Yeah.
And if we go just a little bit outside our solar system, there are also like really, really most promising projects. Actually, this one is a really international, huge one with ETH Zurich in the lead, right? It's Sasha Quantz, who can't be here, unfortunately. He's already with his 4 kids and wife at the holidays. But good for him. This is his project, and it's also kind of a really good mix between Center of Origin and Prevalence of Life and ETH Zurich Space. But maybe just in a few sentences, Didier, what is the life mission?
Yeah, this is a very interesting mission for many reasons. The first one, it's also a jump in technology here, which is being discussed. Instead of having a big telescope, you combine many telescopes, which is a bit of a strategy. is used for other science, which is detecting gravitational waves, which is not telescope in that case, but kind of detector. I think this is growing. It's flying different telescope at the same time. This is going to be. But what is fascinating in this is the idea of that is about 20 years old. About people have started thinking about that. At the beginning, it was seen as a crazy idea, and right now I'd say, well, it's challenging, but it's a possibility for the future, and I'm pretty sure that in 20 years that will become obvious. The reason for that, and it's good to remember, it's technology. I think the progress into science is very much connected to technology. And I come back what we did with Michel, 30 years ago. At that moment, we had two big jumps in technology. Optical fibers that became available for astronomy, and then a brand new kind of computer that was called microcomputer, Sun Microsystem, if you remember this. That was a complete new technology as well, available to lab, and you can process the data in a very different way without going to mainframe. And that was the element that made us beating everybody else, because we had access to technology and we use it well and we implement it well. So I'm really looking forward to the progress and this vision, because this is how it works. And in a sense, Webb, it's a very old technology because it was designed 30 years ago. If you have to restart something like Webb, I'm pretty sure you would use other component. You will start
a different rocket.
Different rocket, yeah.
Bigger one. Yeah. The European rocket is great.
So this is really where it fits in. So this kind of program is exactly the kind of program that drives the vision and the possibility for the future. Whether it will be exactly like that, I don't really know. But what I know for sure, that kind of mission will be flown one day. It's just a matter of time right now. But maybe you have your view on this.
No, my personal feeling is we should be doing, look at through the lens of technology. What you need for that? Really good clocks, laser communication. You need really accurate positioning and flying a spacecraft. All this stuff is what people do around here really well. It needs to be more accurate than this one, clockwise. But so the way you do it, like if somebody says build it today, this costs more than your budget for a few years, Joël. So let's go talk to Parmalin, but or the Bundesrat. But it's not in any way affordable, right? But what we can do is make huge progress. I actually think this kind of the accuracy of how we can fly a spacecraft and how we position spacecraft is massively increasing right now. And it's only two types of spacecraft we need to build. And I think it's absolutely achievable to kind of make massive progress with this. Perhaps the first thing we do is not an exoplanet, kind of image something in the outer solar system, and do it there. But no, we should be making progress. That's what we want our students to think about, this kind of idea, and really start developing the technologies for it. Not just our students, our professors too. Which is where most of the kind of capacity is, of course, in a university like this one.
Yeah, we have many more projects at ETH Zurich. Due to time, we won't go too deep. We saw some of them in the video. Many more are more to come, right? And we have like these two big centers, or one initiative, one center. But just shortly, what is the difference? Or maybe can you just, really shortly, Didier, explain?
Well, okay, I will be very short. Well, I have to say there is an amazing group of people here, and some of them are in this room, and without all these people, it does not work. I think the idea is they share this vision that we can make progress on the origin of life and when we have life in the universe on their own expertise, and they understood that it's even better if they try to communicate and work together. And now we have a couple of departments that is working together, professor in these departments, and we're triggering a curriculum, a teaching program, because we believe that if we learn better to work together, it will be even more powerful. It's a bit the 1 + 1 doesn't make 2, makes 3, really the idea here. And that's what's behind. And the support level is just amazing. And I think this would have definitely not be possible without this momentum, this element pushing for this, and the support also for Schulleitung on that program. So I'm delighted to help to setting this up, and the COPL Center.
Since we had many newspaper articles and stuff about ETH Zurich space in the last year, I won't ask you the same question, but I was wondering, Thomas, once we had an interview, I don't know if you can remember, and then there was Hendrik, that's the Hendrik Holbenbach, who's responsible for the robots in space at ETH Zurich. We have many amazing robots who's going to be in space pretty soon, hopefully, fingers crossed. And then suddenly you asked him, Hendrik, if I would give you $100 million, what would you do with it? And Henry was a bit overwhelmed. It was, of course, the meaning like in his research, right? But I really liked the question. So I was wondering, like, Thomas, if I would give you $100 million, what would you do with it? Of course, here with the ETH.
I always wanted a Ferrari.
Well, you have 100 then.
A Ferrari for the whole group, right? Look, I mean, what I would do get off with an injection of money like this. By the way, I just want to talk about money first. The one thing I've learned both in startups but also with academic programs is the question, if I give you all the money first, the answer to that question actually is more important than, well, how much money do you need? Because what people say, what do you need to achieve this goal? They say money. And then you say, if I give you the money, what are the first 10 things you're doing? And often they haven't thought about it. And so I have not asked anybody for $100 million. But if we got $100 million, what we would do is create initiatives to develop technology, technologies in 2 or 3 arenas. My guess is we would go after technologies of life detection, but also of observations in space. And the third one would very much focus on data technologies relative to Earth science, because I really believe we have a big disconnect. What we have in Earth science is almost the opposite problem than we have elsewhere. We're really data rich and information poor. So we have a lot of data that are coming down, terabytes of data, and we're not giving it into the hands of farmers. We're not giving it into the hands of people who make better decisions with the data. They make more money and help the Earth. They save money with fertilizers, for example, and get more return. So for me, it's that data mismatch that I would go after. So I would, like as always, if I take money, I do 3 things, because one of them will fail for sure, and one of them will be okay, and the third one will be a huge success. So that's what I would do.
What about you, Didier?
Well, I think that it's always what I keep telling when people ask me, oh, what is the level of support that science needs to be? I think science is a marathon. It's been on the long range. It's a long-term vision. So you don't make breakthrough in a day. It takes years to build up. You need to build community. You need to build knowledge. And the typical time scale is a minimum of 10 years. So it's not about the pot of money to boost it. It's having a continuous flow of money that enable a growing development. When you start a program in the unknown, the day after, you've learned something and you say, oh, I've learned that. So it means maybe I need to change a little bit. So it's impossible to plan something which is breakthrough knowledge over this lifetime, because the knowledge is evolving if you do right. So the message is always get a constant flow of money. So if you give 100 millions, I would ask for this amount to be spread and organized, and also to get a legacy element, and to remember the energy and the brain is on the youth. So if you don't give them a chance to achieve and to do things, I mean, you're missing opportunity. So you should find mechanism when the new generation feel at ease to develop their own creativities. And sometimes it's a challenge, it's not easy to cope with systems. Another time it works. So I think we should really think about this kind of way to use the money. And so far we have done pretty well, I must say, with a lot of instruments of money. But of course, if you want to promote some specific area, a little bit of a boost would help, definitely, yes.
So I want to just point out that you hear 2 careers on different continents. Did you notice?
Yeah.
I mean, you're and it's not good or bad, but you have a European career and an American career, right? And so I think what we can do together is do exactly what you said, which create a long-term strategy, but that drives action today. The one thing that happens with long-term strategies sometimes is that it does not drive action today. And so basically everybody thinks we're going to do it later. And what I'd like to do is really create a sense of impatience, not with the result, but with action. Because both, I think, come. Frankly, that's what you did. That's what impressed me about your story, is that you did it with the tools you had. You didn't have the fanciest tools. No. You did not have the fanciest tools, but you had guts, and you did it then, that time, when everybody said you're wrong, and it's not possible. And so for me, I mean, that's what I'm taking from your story. And kind of for me, that little bit of impatience, a little bit of confidence that you just like, why not me? You don't need to be the best, but why not me? Is something that I really hope we can instill kind of in our community, in our students especially, because that's what we need in so many places. I just wanted to point that out.
Amazing. The next question is actually not for me, like some of them. Actually, I asked around our researchers, and also some journalists wrote us questions, so thank you very much to everybody who gave me some questions. This one is from Sasha Kwan. So it looks a bit weird maybe, but it's about Europe. So you said also so many times you came also to Switzerland, to ETH Zurich, to put the space research, not just here, but also in the whole Switzerland and in whole Europe to a new level. So I wonder, or Sasha Kwan's wonders, and me too, what does Europe need to play a greater role in space science?
So I want to just point out that Europe has done many things really, really well. So if you looked at the Earth observing technologies, Europe is really leading the world, right? You're not going to hear from me is like Europe is really behind. Kind of what happens in kind of when it comes to ambitious projects of the type that Sasha wants to do. I think what we need to figure out, kind of coming together with the community, both in Switzerland and beyond, is how we kind of take the courage, kind of bring the courage and try some of these things. LISA is a really good project that Europe is doing right now. It's going to be so much harder than anything they've ever done. And that's exactly what they should be doing. I'm clapping on the sidelines as much as I can. But for me, kind of in Europe, there's a lot of things that you can read. Any newspaper you open up, people write about Europe and the challenges they have. But make no mistake, Europe has a tremendous potential to contribute to that potential that we need to kind of be part of in Switzerland, not in some kind of club of countries, but as a kind of part of the community that is there, because the world needs Europe, very much so. There's many things that Europe does better than anywhere on Earth, and so for me, we need to do it again. Take some bets, but also kind of figure out how we can make decision velocity kind of a little bit higher in some of the areas where there's tremendous opportunity and it's Europe's to lose.
So, due to time, we have to move on to the last section, actually my favorite one, or probably the most important learnings from your lives, from the origin of life to your lives. So I was wondering, Didier, which experiences or which persons have shaped you the most in your life?
Well, I mean, when you have a career in science, you're meeting a lot of people, and most of these people you meet, they are just extraordinary, because there is this kind of common understanding what we're doing. We all like what we're doing, so I think the environment is extremely stimulating. In terms of personal life, I think it's a balance between the kind of quietness you need, in a sense, to think, which is something you may find by doing things, walking in the mountains, or being with your family, trying to get focused a little bit, with the intensity of research, which is a bit like a drug, it's a bit like an addicted activity, and it's the right balance to find. But behind that, there is this strong push, like an artist needs to do art. I mean, a scientist is curious, so he needs to use this curiosity driven. So I always follow my gut's feeling and did what I did, and I never found there would be any limit. So in a way, I understand, and thank you for pointing this. I think anything I did was thinking, okay, maybe this is gonna fail, or maybe people think it's gonna fail, but I still do it. And this program for life, I mean, I started that 10 years ago, and it was a battle to get through. And now it's become much more easy, but early on, we were very few, believing into this. And it's by growing and growing, believing, we start pushing the system. So I think if you believe into something, you should do it. That's just obviously my motto.
And Thomas, what would you say, what are the 3 most important lessons or findings from your life so far?
I think the most important one for me was that you don't have to be successful alone. I just really believe kind of most important things you do, whether it's building a company, whether it's building a research group, even building your own career, there's people by you that will help you. I mean, I benefited enormously from my mentors, and I still kind of ask for their counsel today. So kind of you don't have to be successful alone, and that takes pressure away because you just basically say, hey, I'll just do my best and I'll ask people for help. I think the second thing, which is kind of tough to say, but I would say 80% of good solutions happen because people don't try. So kind of the thing I really hope we teach here is that trying is important, even if it leads in failure. Smart, not stupid trying. I mean, I don't jump out of airplanes that work, right? Kind of, but so people do. But kind of my point is try. 80% of good solutions don't happen because people don't try. And the third one is if you try to do something new, you don't get it right the first time. So kind of innovation and iteration always go together. So kind of some people call iteration failure. I don't. Iteration is learning. It's about doing that. So that's the third one. So kind of if you go on your butt, it knocks you down. You know, it's like that's just part of the process, especially with research. It can be really discouraging. You know, mostly you find dead ends and kind of get back up and do it again. And so for me, the same is true in the innovation game. That's the third one.
Didier, if you could, which advice would you give your, let's say, 30-year-old self?
Oh, advice. Oh my God, this is always, this is so difficult. I think this failure element is something which I think is very profound, and it certainly is something that could be an advice. I think most of the time, I mean, we're failing. I mean, we look very successful right now, but we failed many times, and we keep failing. I think the idea here is failure is part of the process. The failure should not be a showstopper into what we're doing. And sometimes it's a message which is difficult to convey. I mean, it's because when you're bright students, you're not used to fail. And if you want to transition from being a good student into an amazing scientist, you have to fail a lot, because that's the principle of it. Otherwise, you will not be doing the most exciting sciences. So it's part of this process, being able to deal with failure. And whatever happens, you're just responsible for the failure. It's much more easy, because if you treat your failure that way, you always learn for something. So that would be my advice. I mean, don't be shy to fail, because it's part of the process, really. And learn to fail as well. It's a bit like a judoka. You just have to fail. It's part of the process.
What about you, Thomas? Not sure how old are you on this picture there.
What would I tell you? Don't wear golden necklaces. Green hair is also not very cool. No, I think what I would tell myself, and I think it's something I try to tell students, even though you should have an impatience to act at times, that should drive you, whether it's your curiosity, whatever it is, kind of things that matter take time. And there's a natural patience that you need to have. And I did not know that. Like, I made myself crazy for a large fraction of my early life, because I felt like if I had a year where I didn't get promoted, I was failing. And for me, that kind of, that made it harder than it needed to be. Because to a certain extent, again, all important things in life take time. And kind of it's much more important, like you said, keep learning. Like if I interview somebody, for a job, so often I ask, what did you learn last week you didn't know? What did you learn last year that might surprise everybody? Right? Kind of, so for me, I'm much more interested in that answer than kind of whether you know a specific question or a specific answer exactly. Because if I have a learner, somebody who's really curious, has the integrity that I don't want other people in my group, and somebody has of course skills, but that curiosity I interview for, and so for me that's in the long run what makes you successful, and so I wish I knew that.
Thank you very much. We're a bit late, but now we can come to the Q&A session. It will work like this. You can raise up your hand due to time, and because it's fully booked and so many people are here, just one question per person. So choose wisely and choose your best question. Put your hands up, and then I'm gonna pick you like when we were at school. And then you can take the microphone, press it just once, and then you see the red light, and then you can talk and ask your question. And if it's specifically to one person, choose a person, please. I take you, you, I'm sorry, yes, you, sorry. I think you have to...
Yeah, okay. Following up to the point you both made, what would be something that you think is very important to observe, but due to technological but not fundamental physics, you currently cannot observe?
Sounds like a question for you.
Yes, I mean, you're talking about ETH, something that would be here related to ETH. This is Zurich. So why is...
About life.
Generally about life, exactly.
Yeah. What would you like to observe?
Oh, okay. Well, again, that's what I mentioned before. It's not a one shot. There is a different layer. It's a steady approach, and with possible ways to come back and change. So there's a series of questions you can ask to yourself. The first one is, you have to realize that we have life everywhere here. Life is based on the same similar component everywhere on Earth. So why so? Why do you have this way of doing the chemistry? That's one of the very specific questions people would love to answer. It's called the engineering of life, from the chemistry. Now, of course, life to be engineered, you need the condition for life to happen. Well, nobody would agree because it goes back to the very origin of life on Earth, which happened about after 1 billion years after you make Earth, you make the solar system. Not much is known about the situation here. So then you open another question, so what was it? And then you can combine the two and say, okay, how much can you move around this and change the conditions to have some kind of chemistry which is maybe the same or not the same or different? And then what is the impact of this chemistry on the planet? Then you can maybe try to look for it, whether as an ancient trace in the rocks or in the atmosphere, whatever. Frankly, in any of these questions, we don't have any answer right now. But we have ways to make progress, on some of them faster than others, and there's a common understanding that none is, absolutely impossible to solve. They will need a bit of time, but we do have the background right now to make progress. So that's really the main avenue, and there's a long program that we're starting here, and the kind of time scale I have in mind is 5 to 10 years, to get significant progress into that. And then I even made a bet with somebody that within the next 10 years, we may have the foundation of the chemistry for origin of life on Earth, known, at least replicated. That would be a major, major change and into the understanding of life.
Okay, you with the glasses.
Thank you, Anna.
Oh, sorry, I know
no
you.
worries.
Yeah.
Question to you.
Mirko, I'm sorry.
No worries. I have a societal question for you, Mr. Zurbuchen. So coming back to what you said in the beginning about the scientific revolutions, right? Mentioning Galileo, Newton, Giordano Bruno. So of course, scientific revolutions always come with the marvelous revolutions for science, but they usually lead also to quite, let's say, earthquakes in society, right? So the question is rather, so assume you have found life, or then how would you communicate this? How would you bring that to society to minimize the effects on society or maximize?
I really appreciate the question. So first of all, what's really important is to stick to your principles, no matter what the question is. For example, I feel it's absolutely important to talk about science, no matter what you find, in the best way you know how. And we would do the same. And frankly, kind of in my job at NASA, we spend some time talking about that. How do we talk in a differentiated fashion, but we talk about everything? So if we found life, we talk about it tomorrow, assuming that it went through peer review and all these things that the thresholds we put there. What would happen, though, is actually hard to predict. And kind of for me, the obvious thing, the thing I always thought would happen, is that kind of what happened in some of these other revolutions, that people who were deeply people of faith would kind of say, hey, that cannot be because of whatever. And that is not what my experience was kind of hanging out around Capitol Hill, where there's a number of people of faith. The person who was the biggest champion, he basically said, and again, a person of faith, he basically would say, hey, it would make the Lord ever so bigger if we found life elsewhere. And he pushed that, and we had long discussion. It really helped that I knew the Bible from where I grew up. He loved me because I could cite back. I said a verse, I said the next one. You know, so for me, I think it's really hard to predict kind of the macroscopic picture because you don't know which way it would go there. But I think what's important in science, we need to stick to our principles. So I'm really against kind of changing our principle because it's uncomfortable, kind of across the board.
You in the green shirt. I think you have to push the button first.
I have a similar question. You assume that we find life, but then you also assume that on other planets life developed already. Why we never had contact to any life? What's your assumption in this?
It's a very common question. Maybe I can address this one. There is here just perspective. We need to get this into perspective. Let's look at the Earth. So the Earth has about 4.7 billion years of time right now, since the time the Earth was established, was built. We know that we have evidence for life at least for the last 3 billion years. So we know life was on this planet in a similar way that it is right now for 3 billion years, right? Now, how long are we on this planet, our species? 1 million years. Since how long are we starting affecting and changing this planet in a way that we send signal or we do things on this planet? Well, 10,000 years, about the time with the agricultures and all this. So the time scale here, it's massively different. So we have to be careful when we think about life because we tend to see life as us. I think we're just a detail on life on this planet. And it's very likely that in a couple of million years, there will be nothing left on us here. But this planet doesn't care, life doesn't care. So we have to bring back this evolutions of our species into the evolution of life as a general term. So maybe the fact that we're not talking with other advanced level of life, because that moment when you're able to do so, it's a very dangerous moment when at the same time you have the power to self-destructions and to destroy the habitat where you're living. And it's very likely that it's going to happen. Just look at what's going around. And I think the question of talking with a civilization is really a very tiny element here of the global question about life and what is behind. So that's my reading into that right now. And in a sense, it could also be an element of warning for all of us. The fact that we don't have anybody, I think, is tell us very much the fate of us if we don't be careful. So I tend to turn that into a lessons learned for our species of the risk that will just be a very short-lived compared to the global evolution of life on this planet.
I have a very simple, maybe silly question. With climate change going on, do you think we can have solutions to our problems from outside, from the universe?
I can take it. So I think my take on that is rather simple. Climate change is an easy problem to solve because we know exactly what's happening. And we know exactly how to deal with that. But it's complicated to implement because we are a complex society. And you cannot decouple legalistic effect, the economics effect, the sociology response, the psychology of human body, everything goes into that. So it's a very complex program to deal with that in terms of how us are going to change this way of doing. But look at the past. We have done that very efficiently. It's one of these guys that would deplete the ozone. In less than 10 years, I think the agreement to deal with the ozone was reached because it was about dying really on this planet. We would have never done that. Within the next 50 to 100 years, it would be over. Global warming is a bit more subtle, it's much slower, and it doesn't go in the right directions, but it makes maybe the push for implementing the solutions more difficult. But the solution is all known. So it's not about the solution right now, it's how we implement it that may be dealing with maybe human psychology and society organization here.
The lady with the flower top.
Hello, I have a strange question. We all know that our bodies consist of some molecules of different types of cells. Have you ever thought about the galaxies and planets, like they are a small part of something bigger, of bigger organism? Thank you.
Okay, I can take that. Well, no, fine.
I want to know your answer.
I keep telling there is no. Okay, so I know a bit what's behind this is the idea of when you have a very complex system, and you can treat the universe a very complex system, something may happen in a way that the system may be aware of itself on this. I think it's a very nice idea in terms of intellectually. You say, okay, there's a very complex system, and this complex system, there is some organizations, and the system can have some awareness of themselves. Well, the challenge here is the idea is nice, but how do you translate that into an element of fact that can tell you anything, that there is anything real behind that? And unfortunately, there is nothing really obvious that tells us that this galaxy is alive, in a sense, as a system, and we can interact with the galaxies. We have a pretty good understanding of what is in the galaxy to some extent, because, as you know, most of the components of the universe, we have no idea what it is, and it's dark matter, dark energy. It's fascinating physics to understand. But the translations into the aliveness of a human body or what breathes life into the element of just matter is something that we have no way to make these translations. And it has been almost some time ago that we have clearly divided the two, and in the matter and the human soul, this element about that. But there is a lot of philosophical questions you can ask, and you can just think about this and invent words. But the reality is, we have nothing to say really clever on that.
Right now. I just want to point something out. And so I think the thought of kind of being part of something big is a good thought. And it's something that's reality when it comes to where you figure out where you came from. I think the one mistake we sometimes make is the mistake that happened many, many times in history, where people thought they knew everything there is to know about nature. I do not believe that at all. I could easily imagine that some of the questions that come from a question like you're asking, but need to be translated into an experiment that is reproducible in a way that could lead to another understanding of that or other questions that currently is not achievable. So for me, the one thing that I never want to give the feeling for is that somehow we understand nature fully. That has been the wrong assertion for the last few hundred years. So and everybody thought, and then the guy comes like, hey, guy in Bern that couldn't get a job at ETH, Albert Einstein, he said, look at the story. Go ahead. Later, that's right. But like he said, but there's other ways to look at it. Right? There's other ways to look at it. And for me, and then it opened a whole, the beautiful picture with the 6,000 galaxies between the grain of sand, the other thing I could have said, do you see how all these galaxies look totally distorted because of that cluster of galaxies? That's general relativity in action. It's right there, a picture of kind of a theory that many people, I still get emails on a regular basis, people telling me, general relativity is not correct because I have another idea. It's like, it doesn't matter what your idea is. We have so many experiments. My point is, keep looking for kind of new ways of looking at this, but things that can really be in that sense. I totally agree, right? Testable, reproducible in a way, using the tools of science, because there's a lot of mystery still remaining to be discovered. I just really want to say that because there's so many young people in the audience.
You in the back with the bit crazy hair. Sorry. Sorry. No, it's not so crazy.
Hi. I recently started to work in spacecraft exploration, meaning like on producing hardware. And I feel that every time there is a blocking point, meaning certifications, regulations done by industries being ESA and NASA, don't you think that this is a blocking point for innovation?
Yes.
And
no, I mean, look, let me just tell you, most spacecraft that were launched last year were not built that way. Most spacecraft that were launched last year were built with a process that's more iterative, much more lean in its development process. And I want to tell you, there's many things I was successful at NASA. The one thing I tried to do is for cheap spacecraft, as compared to the expensive ones, to basically reduce the process that is being developed, because it's so useless. Why do I know? I built spacecraft myself and space instruments. And in literally most of these documents just have no use. And I tried to reduce those documents. I was unable, like literally. So I'm a strong believer that some of these things need to come from organizations outside. So for me, my wish would be is that some of these things we're talking about in space, we can do independently of some of these agencies. Not because we dislike the agencies, it's because we want to use a different set of processes, show proof that it works, then bring it back to the agency and say, here's another way. And that takes some time, but I totally agree with you. We're currently, by the way, the positive narrative of this, this way of process has created a lot of success. But what happens is process without the reflection of why the process is there becomes a shallow blocker of innovation. And so for me, what happens is as the next generation comes, there's so many processes, people who stand around with notepads and check off boxes. That's not value add. Value add is really trying to understand, use the process, question it, and then move forward. And so, yes, most spacecraft last year were built in a different fashion, and we should learn how to do it here too.
Who else? Sorry? Okay, you. Exactly.
There was another guy with crazy hair up there. Go ahead.
Who is you?
Let's say we do find life beyond Earth. What will be the next questions you would ask if you had found, if it was possible to find life beyond Earth?
Do you mind if I I want to use slightly different words than he's been using that, but I want to say exactly the same, and you push back if I misinterpret. Looking for life elsewhere is not a yes-no question. It's a new way of interrogating nature, asking questions about nature, about the history of planets, about the evolution of certain physical and chemical systems in a way we've never asked before, because it ends up in a different trajectory. If there was life elsewhere, a whole book of questions, okay, so how does it, in what way is it similar or different than our life? Remember, the print, the blueprint of life is this complex molecular structure that's in every one of our every one of our cells that is out there, and also in bugs and microbes around, right? So for me, it's in what way is it the same? There's an infinite number of questions that would have as its consequence a better understanding not only of that, but of us. See, the problem, if there's anything I want us to take away from the story he told us, is that the 2 planets he discovered and the subsequent work afterward changed the entire understanding of the solar system. Because it actually helped us understand what's important, what's not important. There's no way to figure out that it's actually not important that the rocky planets are here and the gaseous planets are here. What's important is to recognize that the solar system, every stellar system, is evolutionary in nature and is changing over time with instabilities and stable parts. That kind of question you cannot figure out in the absence of many stellar systems, which is what he has done. So for me, infinite number of questions, but most importantly, we would look at us in a new way, kind of in a way that frankly, we would have never guessed what questions to ask. Things that we think have to be that way don't have to be that way. And for the first time, we can figure out what's important, what's not important of the things we know. How would you have answered it?
Well, I think this is all right what you said. I think it's absolutely agree with what you said. I just want to give you two additional elements about what. Let's imagine you detect life. Okay, we agree this is life. Well, there will be two conclusions you would draw. If you detect life in the solar system, you would realize the condition for the solar system to produce life, not only on Earth, is met. And you will even start talking, maybe life started somewhere else and moved to Earth, it's possible. So that would be the first element you get. Now, if you start finding life on another planet, you will absolutely have the same kind of rational thinking that we had 30 years ago, that life is a common element of the universe. Because if you find one, it means there are really zillions of them. So that would be the two main consequences. Now, from that, what you will do, you will suddenly ask the questions, does it look exactly the same that this one, and how much could you change a bit the conditions for life, and how likely it is for life to evolve the way we have evolved. But that is possibly what will happen. But we're not yet at that stage, so I think we may have surprises, and I would not be surprised to be surprised here in that topic.
Other questions? The woman, you. With the, I don't know, just you with yeah.
Thank you. Yeah, it's me.
It's you.
Thank you for this presentation and everything you said. It's my first time I heard about your research, but it's very interesting and fascinating. But I thought, how much impact and interference is research to our planet, to universe in general? So if we find the life beyond Earth, what do we do? We leave it, or we gonna stay and interfere with it? Have you ever thought about it? I'm sure you did.
So if I try to summarize, the question is what is the impact of finding life on those civilizations? So should we be afraid of this? This is what you want to know?
More like how much we interfere with natural processes.
Oh, natural process. Well, I think in a way it's too late. We're already interfering with the cosmos, so the way we are. So we already send zillions of electromagnetic waves into the cosmos. So this is the reality. We already interfere in terms of life. We have completely changed the nature of this planet because life is born and part of this planet. So we already interfere. But I don't feel we interfere because we're part of this universe. So I feel life being part of this universe. So it's one of the options of this universe. So there's no interference at all. It is part of the option, the possibility. So I don't think the word interfere, which means something negative, is really valid here. We're just part of the game here. It's part of the possibilities. Now, how we would respond to that? Well, it's a very interesting question because life, I always say the same. So if you imagine a civilizations on other stars looking at us since a couple of billion years, they will be aware something is going on this planet because actually we have this great oxygenation event that produced so much oxygen on that planet that there's only one way to produce such oxygen and maintain it on that planet is to have something alive making it. So it's pretty obvious that something is going on since about 2 billion years. So we're extremely visible on this galaxy since 2 billion years. So if a civilization have the means to travel around, then they had a lot of time to come already to visit us. This is really this. So this is to bear in mind with this element. Now, what it means for us? Well, the knowledge. We're just a fascinating species. A baby born right now will have the same brain that a baby born 10,000 years ago. Exactly the same. There is not a single difference. Well, the knowledge that this baby would capture right now in 20 years would be dramatically different from the one that was 10,000 years ago. So we have a capability to capture the knowledge and to make it us so fast. So the society is evolving with that, of course. The exact response to the society is complex because there's a lot of elements that bring it. But look at the way you're living, how easy using cell phone, how easy using transportation, how simple it is now to use internet. Well, you go back 50 years ago, that was a complete another game here. So I think we are fast learner because the brain is so plastic. So any knowledge, we will capture it right away. Now, what we do with this knowledge, that's up to the society to decide.
Do you mean if I just take a slightly different tack to answering a question that you may have asked? Kind of as we go explore different worlds and different kind of areas, I think the one thing we always want to be aware of that the tool sets we have right now and the questions we're asking is not the last type of tool sets and questions that should be asked. So we want to leave what we're observing in a way that somebody else after us can come and investigate. That's, for example, what we're doing on Mars today. Kind of the way we're exploring as an international community, we're actually being really careful to not bring as much kind of life from Earth with us because we know that kind of somebody in the future might get confused. So the interference that you're talking about is kind of when we explore something, there's a non-zero chance that there is kind of interference in a sense that we're affecting what we're trying to study, kind of a profound idea out of quantum theory, kind of in a direct fashion, but it's happening elsewhere. But I think what we want to do when we explore is always be responsible, kind of recognizing what I just said, is that we may come back with better questions, with better ideas. We want to leave whatever is there in a way that can be studied later on. Whether that's life or other planetary or kind of world environments, that's the same. So I think it's a very valid question in that sense.
So we have just time for one more question because we're over time already. Who has like a really good one? You look like you have a really good one. You with the glasses, Giordano. Sorry. Sorry.
Thank you, Anna. So there is something about searching for life that you don't agree to the other?
I made a joke earlier today, and that is that, Pauli was a Nobel Prize winning professor from here, and I thought there's a Pauli principle with us and ETH. We never are here together, which is, except if somebody says we need to be on stage together. So it's kind of interesting. There's a number of things that we disagree on. You heard kind of the way we should be focusing, kind of we have different ways of approaching it. I think the one thing you should know, kind of when we chat, kind of I know we read the same stuff. He has done, much, kind of he's doing really exciting work. So kind of if there's a question in the science community, we're probably aware of it. So we're not orthogonal in that sense. And kind of once you get kind of deeper in, kind of you need more time to really find the disagreements, and I look forward to spending that time with him, especially as I learn about kind of the plans where we overlap, where our kind of technology and kind of science focus we have on the space side overlaps with him. So at this moment in time, kind of on the intellectual point of view, I haven't found anything that were really divergent, but that's just because we both believe in the power of science.
Well, I have a slightly different take on that. I think there is, we have to disagree, so now, when you're a scientist, there's something which is just fascinating. I can't go in any country in the world. I don't understand the world about what they're talking about because it's big and different languages. But as a scientist, we will understand because we use the mathematics and we have the same way of thinking. And a fact is a fact. It doesn't depend on where you speak and the education you have and the sociological background you have. A fact is a fact, and we are born with that because we just love that stuff. And we share the same kind of way of seeing the reality through the facts. And that's the reason why we don't disagree very much, because the fact is a fact. Of course, some facts are subject to disagreement because some of them are a bit ambiguous. I'm pretty sure that they will be claimed for life detection or for that, and we may not agree that day. You may say, yeah, it's too optimistic, or no, it's not right, and that's part of the process. But eventually, at the end, the amount of fact becomes such, and we can come back 30 years ago, when you have a couple of planets, it's awkward, maybe these guys are not right, there's something wrong in the system. But when you have thousands of planets, you have to admit that there is a real fact behind the solar system is really different. So that's maybe why we get the feeling that we don't disagree very much. But I'm pretty sure if you go to the gritty detail, there will be a lot of elements that will have slightly different take on it. So I trust you, you have a different opinion on some of the elements we're talking about here. But that was not really the purpose here of this high-level discussions. So if we give you this feeling that all scientists agree on everything, this is a wrong feeling, I can tell you. I invite you to come to any scientific meeting. You will see by yourself.
So I have a deal for you. We'll get to know each other for another year, and we'll find the 10 things we disagree. And when Anna is back from her world-around trip, she's launching on, she's going to do a little kind of intellectual fight up here and figure out who's right. How about that?
Thank you so much. Thank you so much. If you have still some questions, you can post them on social media, and maybe you will answer, and maybe not. I don't know. But you can try. At least what you've learned today, try. You know, trying is better than not trying. So before we come to the end, we come to another section, like the most important lessons I've learned. I feel a bit too young to say the most important lessons I've learned from life. You know, it's still far away to go, but the most important lessons I was able to learn from you. And the reason is also like what Joe said, I had amazing 10 years here, and the coolest thing ever could happen to me was working with you in the last years. Well, now it's getting a bit emotional, I'm so sorry, but yeah, you're gonna explore life in space, I'm gonna explore life around the globe, and that's why today's my last day at ETH Zurich. And so I feel really blessed that I could work so closely with you, and I feel also that I really want to share at least some of the lessons. It would take too long to share them all, but at least a few. So I start with you, Didier. I don't know if you can remember when we met the first time. It was probably not. I do. So it was a Zoom call. It was like the post-corona time, and I had the task like to do the communication for your start, and then we had a Zoom call, and I was really nervous. You know, you never have a Zoom call with a Nobel Prize winner, so it was like I was really nervous. I can remember that I put my computer in a really good direction. You know, have like no crazy stuff behind me, and even changed my home office hoodie to some serious stuff. I was like, okay, look at least a bit professional, you know. And then we had this call, and we were laughing for about almost the whole hour, and it was so funny, and I just couldn't believe it. Like I couldn't believe it, and so I really learned from the beginning on that it is literally possible to be a Nobel Prize winner and still be so completely down to earth and so funny. It's such a cool dude. And it was so beautiful. I've never ever imagined this, and it stayed the same, right? And just a few months later, I had the huge honor and even bigger pleasure to make the press conference for your start. Can you remember? Yeah. And it was in the dome, right, on the rooftop. And then it was like, I can remember I had some ideas. I was, again, a bit excited, you know, Nobel Prize is coming, I got a big event. And then you said, like, from the beginning on, like, do whatever you want. You can decide everything, just do it. You know? And I was so impressed because I felt like this huge, huge trust. And we knew each other just for a few months. And I've never ever felt it from somewhere else, like from the beginning on. And it was so beautiful because it gave me so much energy and also so much room for my creativity, and it was a really lovely event afterwards. So I really learned from you how important it is to trust your team members and to let them feel that you trust them and leave them room for their ideas and for their creativity and let them make the decisions as much as you can. So thank you very, very much for that.
Can't wait now.
Well, Thomas. Thomas. What I've learned from you is a lot. Like a lot. We spent a lot of time the last 2 years, the last year actually. I want to pick out just a few things. And one, what was like really, really impressive for me, it was I had also the huge honor to make an event for you because you came, and then it was like I had a special idea. Like I wanted to make this event a little bit different than we usually do for many reasons. And I had this idea, and it's always like when there are so many different organizations and people involved, there are always many people who just, I don't know, who say, why don't we just keep it like we always do it, and it was the same in this time, and there were so many people who just wanted to keep it the same, and I almost gave up, actually, on one point, because I was like, okay, so let's just do it the same. And actually, you were almost the only person who was like, from the beginning on, you stand so much behind my idea, and you pushed it through, and it gave me so much energy, and actually, I think this was the reason I didn't give up, and we made it. 2 journalists are still here, Christian and Joachim, who went to this event. We made like a breakfast really early at 7 o'clock. Yeah, everybody thought nobody will come. All media came in the end, right? And it was so beautiful. And so this taught me how important it is to believe in other ideas, to push them, and to even try them out, even if so many people are against them, because it's always better to try than not to try, and even if it's not a success, you will learn from it, and that, yeah, like, give people enough space to tell their ideas, and then push them to make them happen. It was so beautiful, and yeah, I think it was a lesson learned from my life, so don't give up, and try to keep on your ideas. At least you can learn from it if it's not a success. And the other lesson learned was like, we had so many interviews because, maybe some of you have read it, like the media interest was huge. We had like a marathon, a media marathon, and besides all the technical stuff you explained, and what was also really impressive, I was writing all the time, and actually on one point I was just joining the interviews because I've learned so much every time. I was like, but one thing what impressed me really much, it's like how you could speak so openly about your weaknesses, and about, also like difficulties, and about your insecurities and all this stuff, because I cannot. And so I was completely impressed, and I thought like, how could this be? And I mean, you're a man, and normally women should be, I don't know, and you're a different generation and stuff. But it's so beautiful, and they're so sure that it didn't just help me, what it did, to try to be even more open about difficulties, about insecurities, about different parts in life, because everybody has them. I think it can help so many people if they read it to trust more in themselves, and to, I don't know, move on, even if you have a difficult time, and don't be anxious, and just move on and make the best out of it.
All right.
I won't make it too long, but there are just a few things which I learned from you both. I'm almost at the end, we're almost done. So, and one of the things, it's like how important it is to treat all people equal and all people the same, no matter what function they have, no matter how important they are or not. And in all these years, like, there was not one second when I felt that my opinion is less important than yours, even though I'm like far away from Nobel Prize, far away from another research head. And that was so beautiful. And I know that it's not normal, not everywhere, unfortunately, but you gave me always so much respect and so much trust, and I really appreciate it a lot. And the other thing that I learned, what you both said, that from space, our Earth, our planet doesn't have borders, right? And you both try so hard to connect people and to build bridges. And so I think that's also what we should focus on. Instead of building more borders, building more bridges between people, between countries, between disciplines. And that's what you're doing, and keep doing it. And that we should focus more on our same vision, right? To widen our horizon as humanity, find our origin, the source which connects all of us, instead of focusing on the differences, right? On the borders and on the difficulties. Focus on what connects all of us. That's what I've learned from you. And thank you very, very much for this. And I promise it's the last one. I was thinking about, like, we always give a giveaway present to the lecturer in our global lecture. But the thing is, what I mentioned in the beginning, you have exactly the same research goal, finding the origin of life and finding life beyond Earth, but it's not like this. You have also another goal in common. I don't know if you're aware of it, because actually my work with you and my work with you was closer than both of you, but from now on it will change. But it's sharing. It's like sharing your knowledge and sharing what you've learned with the next generation. So yes, that's your main goal, I guess, I think, from both of you. So I thought it would be much better and fit much better to both of you to give you not a giveaway present, but I call it a share-away present. So I created something special. I know we all like risk, but it would be just too risky to bring it in. So you will find it outside, but we can see it here.
All right.
And I invite you, all of you, you can really eat it. It doesn't look at this, but it's a cake.
Oh,
it is a cake.
right.
And we will find it outside in the reception. So, but before we all go to the reception, enjoy this nice cake and some drinks, I really, really want to also give a big, big thank you to the corporate communication team, to the community and outreach team for the organization, the technical team. Of course, our president. Without you, nothing would be possible here. And thank you so, so, so much. Big, big thank you to the best university in the world, ETH Zurich, for amazing 10 years. Thank you for listening. Thank you for this amazing event. Thank you for making this happening. Thank you so much.
Thank you so much.